Okay, are there any questions before we get started? I just want to recapitulate on 2 points, which is one on slice projection theorem. And we actually demonstrated the 2D case in class and in the lecture notes. Okay, we say that if you take the shadow of this X-ray experiment and Fourier transform the X-ray, get part of the image, and then rotate the experiment, and then you can get the full reconstruction of this. And then we did the 3D case in a take-home exam, where you actually project everything back to a line again. But you can also do the 3D case, and not having to project it on to a line, but onto a plane. Say you have a 3D object. Let's assume that I can draw 3D. That if I have X-ray firm over there, and that this is D prime, this is X prime, this is Y prime. Okay. And that you do this experiment in 3D. Shoot X-ray and then project them into the X-ray film, and then you get a projection which is a function of X prime and Y prime. And then it is the projection of the 3D image, X prime, Y prime, Z prime, the Z prime. If you were to integrate this from minus infinity to infinity, then you get E of X prime, Y prime, where the projection is just an X-ray going through the object, and this projection can correspond to an attenuation in X-ray. And you can also do a very simple trick by Fourier transforming this. If you Fourier transform this thing, then if I do this Fourier transform, then this would correspond to x of kx prime, ky prime. I'm sorry, I need the exponents as well. E to the I k x prime minus I k y prime. If you do this, then you actually get the Fourier transform of kx prime, ky prime. Kc equal to 0. Okay? And then you can again do the trick that if I rotate this experiment, if I were to rotate this experiment, then I can get a 3D reconstruction of this image quite easily, and then reconstruct this thing. So instead of doing it in 2D, 3D in a line, you can also do 3D projection into a plane. Okay? This is one thing I like to recapitulate on. And then another thing that I like to recapitulate on is the physical interpretation of bond scattering and the physical interpretation of bond approximation, and what gives rise to diffraction tomography. Why do we have an answer such as what we had derived? Okay, so what we found in the case of diffraction tomography.
Professor?
Yes?
Question.
Sure.
S of x prime, y prime, z prime is the attenuation profile, right, of the object.
Right. This is the attenuation profile.
So
of the 3D object.
once you have the attenuation profile, how do we reconstruct the object?
You don't have it inside the object. I can't do it inside your human body.
Okay.
But I can get a shadow of the X-ray outside the human body. So this is outside the human body. And you can get this by shining X-ray through the human body.
So all
of course, this is known not to you. Okay, this is known not to you.
No. So if I know S of x prime, y prime, z prime, how do I figure out the shape of the object? That's all.
No, I can obtain this projection by experiment by shining X-ray, 2D X-rays, and get this film exposed. when this X-ray film is exposed, then it's a function of X prime and Y prime, right? And this is done outside the human body. And in the language of inverse scattering, is non-destructive evaluation, okay, non-invasive evaluation. Of course, this is no good. This is radiating, so X-ray is no good. Okay, MRI is better because it's not radiating. So you get this projection, and once you have this projection, you can obtain the 2D Fourier transform of this in one plane, not a slice, but a plane. And then you can rotate the experiment to fill out the whole of the Fourier space, right? And then if you have this object fill out in the whole of the Fourier space, you can do an inverse Fourier transform. Because from this, you are going to get, by various experiments, by rotation, you're going to get this function. And once you have this function, you can Fourier inverse transform it to get this function. Okay, but all this is done outside the human body. You notice that, right? No need to cut you apart and then measure what the 10-dimensional profile inside you should be. Okay? Is this clear? Okay, let's go to diffraction tomography. And we say that we obtain the scattered field at the receiver location to be something proportional to a constant, a big constant, and then some phase constant, and then plus the Fourier transform of the object, Kr minus Kt. Okay, and this has come about from the Born approximation to an equation that looks something like this. Rho r, rho prime, an object function rho prime, and then instead of the total field here, just put in the incident field. Okay, so this has come about from that equation, and this actually is very similar to what is known as Bragg scattering. It's very similar to the physics of Bragg scattering. Okay, so what we are assuming is that the incident field is from far away sources, so that this comes in like a plane wave. This comes in very much like a plane wave, and we wrote the plane wave as, this is what we wrote it as. So it actually is very much like Kt dot rho kind of thing. Okay, so this appears to be like a plane wave, and then we make this thing in the far field approximation so that this part also looks like a plane wave finally, and it will have a plane wave part that looks like e to the I k r dot rho prime. Okay, so you know what Bragg scattering is? Bragg scattering is a case where people in optics what they do is that they make grating. They make grating, and then you shine light on this grating. And you find that at certain frequency, the backscattering is very high. And the backscattering is very high due to constructive interference. You have reflections from all these gratings, but then they constructively interfere. In a certain free phase, when they are phase coherent, you get a good signal back to you. And this is exactly what happens here. You think of this in Born approximation. So you're actually modulating the object with an incident wave. Okay, you're modulating the object with an incident wave. So you can think of this object being written as a linear superposition of gratings of some sort, you can think of this as being equal to some kind of a if you write this in terms of Fourier transform, you can think of this as being a linear superposition of sinusoidal functions. And linear superposition of sinusoidal functions can be thought of as a series of gratings with different wavelengths. Okay? And then you get to illuminate this object with an incident. Okay? And then this is actually OK should be here. And then you can see that only when this K equals to that you have very good backscattering and very good coherence. Okay? So when this part and this part interfere with each other, then it will take out a special component of this gradient. Do you get good scattering? That's what it means. Okay, that's why you have this K of this object should be equal to Kr minus Kt. So somehow you can think of bond approximation as being when you linearize everything and the object is just a linear superposition of some sort of a grating, and then with this grating effect, it's going to scatter only strongly or coherently when this quantity is satisfied. Because of that, then you can do different experiments to pick up different Fourier components of this object. I think Bragg also obtained a Nobel Prize for this work. So even though it seems like a very simple one, he just did some optical grating work, and then he got the Nobel Prize for training. So are there any questions regarding this diffraction tomography, and it can be used to understand synthetic aperture radar and other kinds of imaging modality? Let's see what we can do. Let's see what we can do beyond single scattering. This is assuming single scattering or bond approximation. And let's see what we can do beyond bond approximation. Okay. How do we do the inverse problem when we cannot do bond approximation anymore? Okay, let's see how we do that. So this we will talk about the distorted bond iterative method. And after this topic, I think I pretty much covered everything I need to cover in this book. And I counted all the credit I have towards you in terms of over teaching, I think as extra hours. So I can either stop today, or we don't have to come to class next week. I can keep talking if you want me to lecture something. Okay? So, do you want me to keep lecturing till Tuesday next week, or we can stop after this lecture? If Mike is here, he'll probably say, stop after this lecture. But have you heard of the story of a musician, a professor, and a graduate student?
Yes.
You heard of that?
I guess.
There was a musician, a professor, and a graduate student, all sentenced to death. So when they asked the musician, I'll give you the last wish before you get executed. What would be your last wish? And the musician said, "I'd like to play the loveliest music in the world," and so he got to play his music. Then the professor was given a wish And he was asked what you want to do as a professor before you die. Professor said, I want to give my last lecture, which is the greatest lecture in the world. Then the graduate student piped up, so, no, I want to die before this professor. I don't want to listen to his last lecture. So that was the story of the musician, professor, and graduate student. So I have enough credit, so I don't have to give more lecture than other than this. This will be my last lecture with you. And then, so before the class ends, I'd like you to do the course evaluation. Okay? So if we do not do bond approximation, in general, the Green's function is the Green's function of a background, such as this one, and then times E of R. Okay? Do you need to derive this one, or it's pretty obvious that is easily derived? Do you want me to derive this equation? Okay, let me derive it anyhow. Let's assume that the total field satisfies this equation. Let's assume that mu is a constant everywhere. And that is actually very good in optics. Mu is hardly a function of anything in optics. So only epsilon changes with space. Okay? And then you define a dialectic Green's function corresponding to a certain background. Then let's assume that this background is simple enough so that you know how to solve this dialectic Green's function. And that on the right hand side, we will just have an impulse response, such as this one. Okay, so in order to solve the first equation, you rewrite it. And then on the right hand side, you will have I omega mu naught j of R. And then you put whatever you have that was on the right hand side. You rewrite this equation in this manner, and then you use the principle of linear superposition to write down this equation. Okay, so the dialectic Green's function operating on this source, in the absence of the scatter will just give you the incident wave. And then when the dialectic Green's function operates on that, you do this term over here. This dialectic Green's function can be found in closed form or not in closed form. You might have to find it numerically sometimes, especially if this kd squared is a complicated function of space. You might have to seek this numerically, but let's assume that you know how to seek this equation solution. How do we find the solution to this equation? In the case of inverse scattering, we want to look for this function, O of R prime. Okay, O of R prime. the distorted Born iterative method hinges on the fact that if you make a guess on the background, so that KB square R is approximately equal to K square R. Okay. If you can make this guess so that this quantity is very close to this quantity, then you can actually make this term small. Okay, this term is a scattered field. This whole term is E scattered. Okay. And you can make E scattered as small as possible if you're clever. You can make this close to that. And then if that is the case, the Born approximation becomes good. The Born approximation becomes good, which means that E scattered is in fact much, much smaller than E incident. And if that is the case, then you can say that this total field here is approximately equal to just E incident. Okay, that is called the distorted. Some people call it distorted waveform approximation, and some people would just call it distorted Born approximation. So it's very much like Born approximation when you distort the background so that the approximation is better. So now that if we know how to distort the background so that this problem becomes linearized and easily solved, how do we look for this object function O? Since the Green's function is arbitrary now, it's not as simple as it used to be. Green's function is quite arbitrary. There's no straightforward, simple method to solve this problem. We have to resort to numerical methods. So let's try numerical methods. Let's assume that the incident field is also generated by a point source, so that I can write the incident field. Okay, I will replace it with the incident field, R prime. That is equal to just a point source incident field. Okay, it's generated in the absence of the background medium due to a certain point source A. Let's assume that the incident field is something of this form. Then I can write the scattered field as a function of R and R double prime. R double prime being the transmitter location. And that I can write the scattered field using this integral over here. Then I will have this being my thing over here. I can put a G together. I can lump this G that comes in from here together with that. Times dot with A. Okay, A is just the source that will generate the incident field times the object function R prime. Okay. So you can see that this is in fact something of the form of the R prime operator. Okay, in this case it is a tensor operator. Just a vector operator, sorry, not the tensor. There's R double prime, R prime, epsilon B times for R prime. Okay. Where I call this piece over here is M bar. So this is a linear integral equation of some sort. This is unknown. This is known. I can do this by experiments because essentially it says that I put a transmitter at R double prime, shine a wave in, it could multiply scatter, the wave can multiply scatter inside, and finally leave and then reach the receiver at R. Okay. So I can perform the experiment with different R and R double prime to get the left-hand side. And I only need to evaluate this. This is, of course, is an approximation called a distorted Born approximation. I think the distorted Born approximation by replacing this with E incident. Okay, when it's replaced with E incident, I get this. So I can make this approximation as good as I want to if I know how to guess the background. The key is to solving this equation. This equation, it turns out, has no unique solution. It's ill-conditioned. So you can hide scatterers in there, and it will not adhere. It means that if you write this into by the usual process of subspace projection method, okay, by the usual process of the subspace projection method, you will convert it into, say, A dot x equal to B. And if it turns out that A inverse does not exist. So it's not as easy as solving integral equation or some of the other equations that you had before. Let's discuss why the inverse does not exist and what we need to do in order to make this problem unique. So because the inverse does not exist, we have to resort to using optimization in solving this problem. And we write a function now that is a function of the norm of the object function. This part here can be modified accordingly. Okay, you can write a function of I that is proportional to the norm of the unknown plus the solution to this integral equation and its norm. Okay, and a sum over all possible transmitter and receiver location. Let me assume that this experiment is done with different Ri and Rj. I just do the experiment and obtain this data over here, and I want this answer to be as close as possible to the predicted result by modeling. Okay, so I define this function now. Because the solution is non-unique, I have to use this function now to find the optimal solution. Okay. Then the next thing is actually to minimize this function now. Minimize this function now so that the solution could be found uniquely. So I do very much like what I did in the subspace projection method. I expand my unknowns in terms of a basis set. Okay, I can expand my unknowns in this manner. And then substitute in my unknown into here and see what kind of equation I could get out of it. If I do the substitution, then the function of I just becomes delta t, and then n and m. Okay, I can also substitute 1 and m as a dummy variable. Okay, and then substitute in the sum. This will have two sums because of the square term over here. Because of the square term, I have to multiply by its complex conjugate. So I take the complex conjugate of this multiplied by itself, then I get product of two series. That product of two series will appear like this. Because this is equal to OR times OR complex conjugate. Okay, equal to that. So when you multiply this with this complex conjugate, you get this thing over here. And then you can have this integral as we had before, and then the product of the basis function. And let's assume that the basis functions are real, so that you don't have the complex conjugated. Okay, so that's what happens to the first term. And then the second term, you would have things like the scattered field, Ri, comma Rj, just like we had before. And then what we have here is that when we substitute this in here, you will get only one sum at this point. I will get the sum over A and the R prime and R, Ri, Rj, R prime epsilon B dot with B n of R prime. And then I put the magnitude square. Okay, we'll just get this one. And I can call this piece over here BNN. Okay? I can call this piece over here. This actually is a vector quantity. This is a vector, sorry. It should be a vector. Okay? I can call this piece the vector E sub k. K is just the order pair ij. Okay, k represents this index I and j. I just got E sub k. And then this can be written as kn L k n. This is the vector. Okay. This when you integrate out, Bn is known. Okay, this is known. These are the basis functions that we have chosen. So this would be known. So this matrix is known. It's also called the Gram matrix. It's known, and this part is known. So this entire piece here can be evaluated into a scalar number. Okay, and this scalar number has index of I and j, and I lump that into k. And then it has an index of n. So I have this as my equation. And finally, the equation I have looks something like this. It's delta t sum of n, m, a, n, a, n, b, n, n. Okay, that's the first part. And then the second part would be something like sum of n, sum over n. Okay, ek minus a n l k n. Okay, so this is what this becomes. The function L just becomes that. And the unknowns are this. These are the unknowns. This is also the unknown. Okay, so unknowns appears here as well as there. And how do we solve this equation now? How do we solve this equation? We solve this equation by optimization method. And you solve this equation by seeking the minimum of it. Okay? You solve this equation by seeking the minimum of this thing. And let's see how we can do this. So I believe the first term can be written as A transpose B dot A. You can write, if you put this into a column vector, you can write this as A conjugate transpose dot with B dot with A. Okay? The second term can we do likewise. It can be written as the matrix L dot with A minus E k. I have to sum over. Sorry, I think the sum actually is over here. Sum of n and this is sum over k. Okay. So this should be equal to the sum over n can be written in this manner, and then the sum over k can be written in this manner. So this matrix system can be written as such. And A is my unknown. Okay, A is my unknown. And K is the sum over all experimental data. When I sum over R and J, and sum over all my experimental data. And they like to minimize this equation over the sum of all experimental data. Okay, this is like a scattering operator operating on the unknown scatterer. And this E sub k, yeah, this should still be E sub k, right? It should be a function of k, okay? So that should be so how do I solve this equation? How do I solve this equation? I can write this equation in the manner that is